both of those theories that kind of conflict with each other in certain senses, in certain cases. But Stephen Hawking had to be a good student of both general relativity and quantum mechanics in order to talk about, hi, mama, in order to talk about and in order to discover radiation from black holes and the black body radiation from black holes that he worked on, called Hawking radiation. It aroused a lot of opposition initially because it upset the existing viewpoint: how can a black hole emit anything? When I first announced the results of my calculations at a conference at the Rutherford Appleton Laboratories near Oxford, I was greeted with general incredulity. So people were incredulous that, this guy is talking about black holes emitting something. But of course, if you listen closely, he's talking about those quantum fluctuations near a black hole and the particle antiparticle business, which, once you come to think of it, it's actually nothing more bizarre than what quantum mechanics very much offers in the form of its sort of probabilistic nature and fluctuating sort of fluctuations, probability. These are all very much within the realm of quantum mechanics. These are all allowed in quantum mechanics. So, and if you're considering, some particles being emitted and getting some low temperature associated with especially the bigger black holes, then it's not so ridiculous at the end. At the end of my talk, the chairman of the session, John G. Taylor from King's College London, claimed it was all nonsense. He even wrote a paper to that effect. However, in the end, most people, including John Taylor, have come to the conclusion that black holes must radiate like hot bodies if our other ideas about general relativity and quantum mechanics are correct. Thus, even though we have not yet managed to find a primordial black hole, there is fairly general agreement that if we did, it would have to be emitting a lot of gamma rays and X-rays. So if you see a source of a lot of gamma rays and X-rays, it very well could be a primordial black hole. So pay attention if you come across that. It's either some illegal nuclear weapon testing or a primordial black hole. I guess both are quite interesting to chance upon. The existence of radiation from black holes seems to imply that gravitational collapse is not as final and irreversible as we once thought. If an astronaut falls into a black hole, its mass will increase, and we mean the black hole's mass. God bless the astronaut. They will cease to survive, I suppose. If an astronaut falls into a black hole, its mass will increase, but eventually the energy equivalent of that extra mass will be returned to the universe in the form of radiation. Thus, in a sense, the astronaut will be recycled. Nothing is really for free. Even the black hole has to pay a price. It's like lunch for the black hole, this astronaut, but then the black hole has to pay a bill as well. There are no free lunches in this universe, even for black holes, apparently, according to Stephen Hawking. What's up, Slapchop? Ask your question. It would be a poor sort of immortality, however, because any personal concept of time for the astronaut would almost certainly come to an end as he was torn apart inside the black hole. So now the other thing is that even though the black hole may pay a bill for its lunch, which is this astronaut, it's not like the astronaut really gets to have an enjoyable time anymore. In fact, the concept of time is done for the astronaut. So Stephen Hawking said, the Big Bang is a singularity which started off time, and black holes are a singularity that end time with their very high gravitational field. So time just kind of stops. Regardless of what you saw in Interstellar, time is no longer a thing in the black hole once you're in it. So even the types of particles that were eventually emitted by the black hole would in general be different from those that made up the